Good afternoon. Today we're going to start a new stage in this course. So the last 2 weeks we've been looking at the basic elements of Python as a programming language. And now we're going to start looking at more realistic examples and how to use libraries to speed up what we need to implement and to make it easier to use, for example, spreadsheet files, databases, plotting, things like that. So most of the examples from now on will be focused on using the libraries and on details that come up when we deal with more realistic data. But today I am also going to talk a bit about some basic ideas of how to organize our code and our data. So basically the fundamental idea here is that we're going to read our data from somewhere, so either from an internet server or local files or something like that, and we need to organize it internally inside our program. And the way we're going to do that is we're going to think about how we're going to organize the data, what kind of structures we will have to organize our data. We read everything into those structures, and then we work with that data in memory. So this will be the solution for most of the problems you're going to meet. The only exception is when you have too much data and you cannot load everything to memory. So in those cases, you probably need some specific solutions, but for most applications of the kinds of things that we are concerned with, you will load your data into memory and then work with the data there. So our programs will usually be conceived and structured around the way we store the data and organize the data. So to see an example of that, we're going to read a series of Excel files and organize the data with dictionaries, and then use the Numpy library to extract arrays, matrices with the data that we want. So I'm going to use data from Gapminder. This is a great site for indicators on country development, things like life expectancy, exports, imports, GDP, and so on, population, etc. So you have there not only the data, but also visualization tools and ways of viewing the data, also tutorials, lectures, and so on. So I actually recommend that if you're interested in these kinds of things, even outside the course, this is a great site. But for our purposes here, we're going to look at some indicators. So specifically, I'm going to use for these examples GDP, life expectancy, and population. And we can access the data online, or we can download either as CSV or Excel files. So usually CSV is a more open format, but we are also going to work with CSV several times. So I downloaded the Excel files just to show you how you can read Excel files with Python, because lots of people use Excel, and often it's the case that you have your data in XLX files to read. So this is the structure of each of those files. We have the top row here with the years. In this case, this is for life expectancy. So the first column has the names of the countries. The top row has the different years for which we have values. But we don't have values for all countries for all years. So in some cases, we have an empty cell here. So this we need to figure out a way of storing this data in our program that can account for this peculiarity. So not only the way we read from the file, all the files of the different indicators have this structure, one top row with the years, first column with the countries, and then the values, and they can have missing values. So we're going to think about how we can organize the data so that we have, for each country, we know for each year what value corresponds to that year. And one intuitive way of doing this is using dictionaries, because dictionaries make it easy to match keys and values. So we can do that for the years. We can match each year to a corresponding value, and then we can have a dictionary for all the years and match that with a country. So we can have a dictionary of dictionaries, and we can build a structure like a tree with our data. So that will be our approach here. So if we use dictionaries, we have one dictionary with each country as a key. So we can access data from Portugal, for example, by going to the dictionary for gross domestic product and using the name Portugal as a key. So this gives me the data associated for Portuguese GDP. And the value I have associated to each country is another dictionary that has years as keys, and the value I extracted from the Excel file as the corresponding value. So if I want to know what was the Portuguese GDP in 2010, I can access the Portuguese data by using Portugal as a key on the top dictionary. And then since this is a dictionary of years and each value corresponding to each year, I can then access the year I want with the year there as a key. So this gives me Portuguese GDP for 2010. So this is a convenient way of storing data because it's easy to account for missing data. I don't put an entry into the dictionary if I don't have data, and so if I try to access data from a cell that does not exist, so a year that I don't have for Portugal, for example, I get an error. There are some other ways of dealing with missing numbers, for example, putting a 0 there or -1 or things like that. But those, you need to be careful when using those because they will work as if it was an actual value. So if you are computing averages or doing something like that, then the computation you are doing will take that value as a real value and may make things go wrong. So this way we organize our data in memory so that missing values are actually missing. If anyone tries to access them, they will get an error saying that the value is not there. And then people can think about how, for each particular case, we can think about how to deal with missing values. So this is what we're going to do. We're going to use the Excel read library. This is a library that allows us to read Excel files. And since the files have this organization, so we have all the years in one row, and then we have all the values for Afghanistan in the second row, and then Albania in the third row, and so on. So we're going to read these files row by row. This would be the most practical way of reading the data from these files. And since this Excel read gives us a function that allows us to read from an Excel file, get a spreadsheet from the file, and then look at the value in each cell, we can create an auxiliary function that just reads an entire row. So if we give it the object for a spreadsheet and the index of the row, this function will return all the values in that row. And this will make it easier for our main function here, because then we just go row by row on the spreadsheet, take each one as a list of values, and organize things as we want. So this is the plan for the program. So remember this before you start implementing something, especially when you start dealing with more complex problems, more realistic problems. You should think a bit about how you're going to break down your program to make it as easy as possible to implement, to test, to implement, and to basically build each of the pieces. And sometimes it pays off if you just wait a day or two just to think about things, different ideas and so on. And when you have a clear idea, start working. If you try to force it, most of the time you end up wasting a lot of time by starting to do things that are not very, are too confusing or are difficult to implement and so on. So we're going to break this down into two functions, and here is a few experiments we can do to understand how the Excel read library works. So I imported the Excel read library here, and I'm going to use this open workbook function on the Excel read library to open this Excel file. So data is the folder where I have all my Excel files stored, and inside that folder is an Excel file called gdp.xlsx, which is the one I downloaded with the GDP for each country. So with open workbook, I get an object that allows me to read, to access the data in that file. And what I want from this object, which is an object for the whole Excel file, so an Excel file can have several spreadsheets. I want the specific spreadsheet that has the data I want. But since all these Excel files only have one spreadsheet, I can just get it by index. You can also get a spreadsheet by name if you're not sure where it's placed, but you know the name. So I'll get just the first one because it's the only one that's there in the file, and I get it by the index 0. So this object sheet is the one that allows me to look at the rows for each cell, or look at the cells of this spreadsheet. Okay, so now I'm going to give this object to the getRow function here, and this function will use this cell value method of the sheet object. So this is the basic method that you can use to look at a cell. You give the index of the row, the index of the column, and this returns the value in that cell on that spreadsheet. So this getRow function, what it does, it starts with an empty list, and then for each column that has values in my spreadsheet, and I can know how many columns there are with values by looking at the ncalls, the number of columns attribute on the sheet object. So this sheet object is what I get when I ask for a specific spreadsheet from the Excel workbook. So I'm going to run through all the columns, and for the row that I was given, so this is the index of the row we want, I'm going to look at the value of each cell in that row by iterating through all the columns and append that to the list of values I started here. And then I will return the whole row. Now we can test this, for example, if we have the GDP data, when we ask for the first row in this spreadsheet, that's row with index 0, we get the first cell, which is country, because then below this we have the column with the countries, and here are the years, 800, 801, and so forth. If we get the second row, then we get this sort of data that we have here. So this is for Afghanistan. In this case, this example, it's life expectancy, I think, and this one is GDP. So this is GDP for Afghanistan. Actually, this was per capita GDP. I think I used another file in the meantime, but it has the data that we want. If there is no data, so if we find a cell that is like this, what we get is an empty string. So if there are numbers, the cell value function converts into an actual number, a Python number. If it's text, then we have a string. So that's what happens here in country, Afghanistan, and so on. If it's an empty cell, we get an empty string. So we can now use this function as a helper function to write the function to load the file. So this function will receive the name of the Excel file we want to load. We have the doc string here. We will return a dictionary with, for each country, another dictionary of years and values. We start by reading the Excel file and get this book object, which allows us to interface with the file. And we get the first sheet. So by index 0, the first sheet is the one that has the data we want. And now we get the first row here. So this will give us this row with the years. But we want to skip this header cell here that has just that string. So we want the first row, but only starting from the second cell to the end. And this is a list of all the years we have in that file. Now we start our dictionary, our empty dictionary, and for each row in our spreadsheet, starting from the second row, so we start with the row of index 1, because that is the start of the actual data. Index 0 is just this header with the years. And so starting from that row, the second row, we get the values on that row. Note here I am iterating through all these values with this variable. So this will be row of index 1, 2, 3, and so on as I loop through this for here. And I'm going to get the country name. The country name is the first cell on the corresponding row, and the values for that country are all the following cells. So from the second one to the end. And then here we build the dictionary for this particular country. We start with an empty dictionary, and for each index of this values list, I'm going to check if there is something in that cell. So if the value there is different from an empty string, I will add a new entry to my dictionary, which has the corresponding year and the value I find there. So what I need to do here is to have a loop that will go through each column and match each year to the corresponding value. So the first year on the list goes with the first value, the second one with the second value, and so on. This is something that occurs very often when you have to run through two arrays in parallel, and that's why in this case I'm using range here. So because I need to use the same index both for the value and for the year. The reason why I'm using the range function here is because the getRow function also needs the index. So since I need the index here, I use this kind of loop. Remember, if you just need the value, you can do for in some array. If you need the index, you can use range and use the length of the array. So basically, this starts with an empty dictionary. For each country, it creates a dictionary of year and value for the country. And then this dictionary of index indicators is added as the value of the country. So we create a new entry in our table with the name of the country and associate it with the dictionary of the indicators per year. And now we return the table in the end. So we can test our function. We'll load the file. The file is in the data folder. It's called gdp.xlsx, and we'll load it here. And now we can see that GDP of Portugal, we get the whole dictionary. This is much longer. I cut it there. And then we can get specific years. Okay. So now we have this working. We could load all the data that we have instead of just one single file, because the idea here will eventually be to correlate different indicators, for example life expectancy with GDP or things like that, and for that we need to have all the indicators loaded so we can look at the data. Since we have all files in the same folder, this is a common solution. You have a set of data files, you put everything in your data folder, and now I can write a function to read all the files in the folder. I don't have to tell the function which files I want. I just tell the folder what folder it is, and the function reads everything. So this is a common trick when you have lots of data files. You don't have to keep specifying each file individually. So we need two things here. First, we're going to use this glob library, which is very useful for looping through files in a folder, because the glob library has another function also called glob that can take as input a specification for a set of files using wildcards. For example, if I write data/star.xlsx, this means anything.xlsx inside the data folder. So this way I'm asking for all the Excel files inside the data folder, and I get a list of the names of all the files inside that match this expression. So this is very handy when you want to read a number of files. Just put everything in a folder and use glob to get the list of file names from there. Now we'll also need to associate each of these dictionaries that we get for each indicator. We're going to organize them in a larger dictionary that has one of these for associated to each indicator. And we're going to get the key, the name of this indicator by looking at the file. So for example, if we read gdp.xlsx, this is called GDP. This one will be called pop, and this will be called life for life expectancy. So we also need some way of extracting that part of the file name from the complete path and the file. The OS library has some functions for the operating system, and those we can use those for this. So in the path module, the base name function takes in a file with some path, with some folders where the file is in, and returns just the file name. So it removes these folder names. The split extension, the split text, will separate any file name into two parts, the extension and the root of the name, so the main part of the name. So if we do this, if we split and take the first element, the element of index 0, we get just the name of the file. By combining the two together, we can take any name for a file with a complete path, take only the base name of the file, so only the file name, and then split and take only this main part of the name. So this is what we're going to do to get from each file name the key for that dictionary, the identifier for this particular indicator. So here is the function to read everything. We already imported Excel read, that one was here before. We now import the OS and the glob libraries. This is just the previous part, so note that these are changes to the whole script. Okay, we started with this, then we wrote the getRow function, the load file function, and this is all here above the load all files function. But this is just to remind you that it's useful to have all the imports at the top of your script, because then you know what libraries you need and what names you're already using for external methods, functions, objects, and so on. And now this is the function to load all files. It receives as an argument the folder where all the Excel files are. And then for each file there, and we know what Excel files are there by using this glob function. So we get a list of all the Excel files inside the folder. And here I'm using another function from the operating system library, the OS library. Because when you have to create the path for a file, you need to put the folder and then this separator. So in Linux it's a forward slash, in Windows it's a backward slash, although if you use it a forward slash in Python it also works, and then you have the file. But you don't know if someone gave you just the name of the folder or the name of the folder plus the separator, or what kind of separator they gave you and so on. So to avoid having to check everything like that, it's a bit risky just to add the two strings together, because if the separator is missing then it will be the wrong file name. And so it's less risky to use join. The join function from the path module will check what we need to do on the folder name to join the two things together and get a correct path like this. So given the folder, given all given the folder that we have, we're going to add or join to this folder this mask here. So this expression that allows us to look for all Excel files. So anything that has this extension. And then for all of these files, we're going to get the name of the indicator by doing this operation here. So we're going to remove or to extract from that complete path just the main name of the file without the extension. And we're going to add an entry to our dictionary, to our data dictionary that starts empty, an entry that has the indicator as a key and the result of loading the file as the associated value. So we get this dictionary of GDP, for example, associated with the GDP entry in our main dictionary. And we do that for all the files. So if I do this for my data folder, where I have these 3 files, I will get a dictionary with these 3 entries: GDP, POP, and LifeExp for the data on the 3 indicators. So I can get from this data dictionary the data for GDP in Portugal in 1980. So since these are all dictionaries, I can walk through the dictionaries and get exactly the items I want. Okay. So this would be GDP in 1980, this would be population in 1980, and I could use this, for example, to compute per capita GDP. Actually, I think this was per capita GDP. I ran this with GDP and also per capita GDP, so the examples may be a bit mixed. I'll fix this later. But this is the important thing. This is the general idea that by nesting the dictionaries, we have a way of finding whatever data item that we need just by specifying the different keys on the different dictionaries. Okay, so now let's say we have this structured in this way. We can easily access each individual item in our data, but we don't have an easy access to, for example, all the values of GDP in Portugal between 2 different years to compare with Spain and France and Germany and so on. So it would be good if we could also, from this structure that we have, in which we have our data, we could extract tables with some views, some parts of the data that we're interested in. So in order to do that, we're going to use the Numpy library, and Numpy has a very useful object, which is the n-dimensional array that stores an n-dimensional matrix. It can be 1-dimensional, a single vector, 2-dimensional, 3-dimensional, whatever we want. And this is useful because it not only stores the array of numbers and allows us to access specific parts of the array, but also allows us to do some operations with the array without having to use loops, so operating on the whole array at once. This is a few examples of what we can do. So we import NumPy. Typically, when we import NumPy, we'll give it this nickname NP to make it easier to type when using the different functions there. And we can use these ones or zeros functions to create arrays filled either with ones or with zeros, depending on the one we use. And the argument that we give is the shape of the array. For example, if we give just a number, then this will be a 1-dimensional array, and this is a 1-dimensional array with 5 ones. If I use zeros and I give a tuple with 5 and 5, this is a 2-dimensional array. This is the number of rows, the number of columns. If I give more dimensions, I get an array with more dimensions. So these are 2 ways of creating these arrays. Another way is to create an array from lists of lists or lists of tuples. So if I have a list or a tuple with different elements, with a number of elements, and the elements are all iterable also, so lists or tuples, and all of the same size, then NumPy figures out what is the dimension of the matrix and give me the corresponding array. So for example, this is a matrix with 2 rows, 1, 2, 3, and 4, 5, 6, and each row has 3 columns. So as long as everything fits nicely, this gets converted into a b-dimensional matrix in this case. Now, what we can do with this is, first of all, we have all the information on the size of the array, the type of values there. So you can use the data type attribute here to see what type you have, and this type is determined automatically depending on the values you use. For example, if we use integer values, we get an array of integers. If we use values with fractional data here, fractional numbers, we get an array of floating point values. We can also convert them. So if we use the as type function, we can convert between the different types. We get a copy converted, and we have in the shape attribute the dimensions of the array. So if I want to know how many rows I have in a matrix, I can look at the first element of shape. The second element gives me how many columns. If the matrix has more than 2 dimensions, then I'll have more elements on the shape tuple. And I can use these objects, the array objects from Numpy, to broadcast operations. For example, suppose that I have this array here. This is a matrix with 3 rows, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if I divide by 2, then Numpy will divide each element by 2. So I can apply this operation to all the elements in the array. I can even add arrays to arrays. So this kind of broadcasting, the only rule is that when we start matching by the last dimension, we get the same size of the arrays until one has size 1, and then it broadcasts like this to everything. So if I want to add these values to each row in my matrix, I just need to do this. This will be broadcast through all the rows of the matrix. Since this has 4 elements and each of these rows has 4 elements, this will match. And now I add this array to the first row, to the second row, and then to the third row. So this makes it easy to do this kind of operations in one go with lots of data. Numpy also has useful functions for dealing with these arrays. For example, I can get the total, the sum of all the elements in an array, the mean, standard deviation, maximum, minimum, and so on. And I can even do this in specific directions by indicating the axis argument, in the axis argument where I want, in which direction I want data to be aggregated. So for example, if I want the maximum value of this matrix here along the first axis, so remember that index 0 is the first element, the first axis is the rows axis, and so I want the maximum along the row, projected along the rows. This will give me as many values as columns that I have here, and will give me the maximum for each column by projecting along this axis. So when we're using this in 2 dimensions, this seems like doing it the other way around. It seems counterintuitive that I'm putting the rows to get the maximum of the columns. But you have to think of this in n dimensions, and in n dimensions you must be projecting along one direction. So if I project along one direction, I get along that direction the aggregate, but keeping all the other dimensions the same. So if I want to do it this way, get the maximum of this row and the maximum of this row and so on, I have to project in the direction of the columns, and this is what I do here by using axis 1. So axis equals 0 will be the first dimension, rows, axis equals 1 will be a projection along the columns. And I can do sums, maximum, mean, and so on. All of these aggregate functions in Numpy can take this additional argument to specify a direction. If I omit that argument, then it's the same as having no direction, so it will just give me a scalar value by aggregating all the elements in the array. Now, just a small detail here about Python. These small details will come up occasionally. We can have parameters that have default values. For example, in this test size function, that's not particularly useful, but just to illustrate, I receive a number, I have a minimum value that by default is 1, and a maximum that by default is 10. So if the number is greater than the maximum, it's large. If it's smaller than the minimum, it's small. Otherwise, it's a medium number. Since these parameters here have a default value, they can be omitted when we call the function. So when I call test size 5, the number is 5, the minimum value is 1, and the maximum value is 10, because I did not give any arguments for those parameters. If I give arguments to the parameters, then they supersede the default. So in this case, the minimum value will be 6 because I'm giving it as an argument. The default will be ignored. And you see that if I give 5 here, it will be between 1 and 10, so it will be medium. But if I add this 6 for the minimum value, the response will be small because now the minimum value is larger than the number. Okay. And I can also give both values here. This is especially useful if we combine these default values for the parameters with providing the argument by name. We can, if we call a function like this, then the arguments are placed in the parameters in the same order. The first argument for the first parameter, the second one for the second one, and so on. But I can specify the values, the arguments for the parameters by giving the name of the parameter. For example, test size 15, max val 20 will omit the minimum value. It's not given here, so this one will be 1, which is the default. And this last argument, the second argument here, the 20 will be placed in the max val parameter because I'm specifying that I want this value to be placed into that parameter. And you can do this by changing the order, doing whatever order you want. The only restriction here is that if you are providing arguments by position and by name, then you must provide the arguments by name after providing the ones by position. You cannot first provide by name and then by position, because then the interpreter will not be able to know what that position corresponds to. Okay. So this is the only restriction. Otherwise, you can provide everything by name if the function allows it. So this is what we can do here. We can give as the first argument the array for the max, the mean, the sum, whatever we want, and then specify the axis to be the one that we want. We'll see this in particular when we use functions that have lots of parameters. Usually all the parameters, or nearly all the parameters, will have default values, so we can ignore them. But if we want to change something explicitly, we can add an argument by name and change that specific parameter. Another advantage of the NumPy arrays are that we can also index the elements of the arrays with Boolean arrays. So let's say we take an array like this and we compare this to a number. For example, this vector larger than 1. The result of this, what NumPy will do is to compare each of the elements of the array with the number I'm comparing to it, so in this case 1, and return an array with the same dimension with Boolean values. So it's false for this one because 1 is not greater than 1, but it's true for these two. And I can also use these kinds of arrays to index parts or my arrays, the complete array or part of the arrays, as long as what I'm indexing has the same dimension as the Boolean array. For example, this matrix has 3 rows. So if I use a Boolean array of 3 elements, I can use that to index the rows of the matrix. And this is a way I can use for indexing arrays. Instead of just having one index like we have in lists, if I have a 2-dimensional array, I have 2 indexes for the rows and the columns. So in this case, I'm saying that I want the rows where this vector is larger than 1. So the rows that correspond to this vector being larger than 1, and all the columns. Since this is false, true, true, this will give me not the first row because there's a false there, but it will give me the second and the third row. So I have this part of the matrix here. I can also take this matrix, for example, compare it to 4. I will get a Boolean array of this shape, but with false and true depending on whether each element is greater than 4 or not. And when I index this matrix with that Boolean array, I just get the values of the cells corresponding to a true value in this comparison. So in abstract, this is a bit complicated in the beginning, but I just wanted to go briefly through this so that we can bear this in mind in future examples, because eventually it will start to become useful when we want to select specific values, sets of our data, and so on. So this is basically what you can do with Numpy for dealing with matrices of data. And now we're going to go back to our Gapminder example. And since we want to compare countries on a given indicator, it's more useful if we can get a set of values in a Numpy array where each row corresponds to a year and each country is in its own column. Because then we can do averages, we can take the maximum, we can select the data and so on. And after the break, we'll see that we can also plot the data easily like that. So one thing that we need is to make sure that we get the same years for every country and all in the same position, because if we don't do that, then we can have data for some years in one column and an other set of years in another, and then we cannot compare everything. So basically we need this function that will receive as arguments the data dictionary, the one that we created with all the indicators, the indicator that we want to extract, a list of the countries we want to look at, and a list or an array of years for which we want the data. Now there is a problem, a potential problem here. We may be asking for years and countries for which there is no data. Sometimes their data is missing in our dictionary. So what we want is to represent this in a matrix, but whenever data is missing, we will use this NaN, this none constant from the Numpy library, which stands for not a number. This is a special representation of a number that indicates that it's not a number. It may happen when, say, you divide by 0, or you have missing data or something that cannot be converted to a number, something like that. The reason for this is again that it's best to explicitly indicate what data is missing than to just cheat and put some, say, a 0 or something like that, because then it can mess up with some calculations, since we don't know that the data is missing unless we explicitly check it. So we'll do that. We'll create a matrix where for every missing data item we'll have a none. And this is the function. So we get the whole data dictionary, the indicator we want, a list of countries, and the years. What we start with is with this values matrix that will have a shape of as many rows as we have years in this array, and as many columns as we have countries in the list of countries. And we want this matrix to start filled with the not a number value. So we can use the full function on Numpy. The full function takes the shape of the matrix and the value we want to fill the matrix with, and returns a matrix with that shape, all filled with that value. So our matrix starts filled with not a number. Everything where data will be missing, it's marked with this special value. Now for each row in the matrix, we need to pick the value for that year for each country. And so in this case, we need the year and we need the index along the array of years, because the first year corresponds to the first row in the matrix, the second year to the second one, and so on. So in this case, it's useful to use the enumerate function. So if you remember, enumerate takes some iterable and outputs a tuple for each element of the iterable with the index and the value. So it will be 0 and the value of the first year, 1 and the value of the second year, and so on. So this is very helpful in these cases where we need both the value and the index. So for each year, we get the index of the row and the value of the year. And then we also do that for each country. We get the index of the country, because this will tell us which column we have to fill in our matrix. And we get the value of the country because we need that to look up in our data dictionary. And now we check if this year is present in the dictionary for this country in this indicator that we want here. If the year is present, then we get the value from that year, for that country, and we put it in the right spot in the matrix. So this is the row is determined by the index along the array of years, and the column is determined by the index along the array of countries. Note that if this condition is false, if the value for this indicator for that country does not exist in that year, then this will not be executed, and the original value in that cell, which is the not a number, will remain there. So all the not a numbers will mark the spots where we have missing data. So now we can test. We load all the data files. We get a list of countries, for example, Portugal, Spain, Italy, and Greece. And then we also create a list of years from 2000 to 2011. And now we get the indicator values for these countries, for these years, for GDP. So remember that we loaded all the data in our folder. So we have GDP, life expectancy, and population. But now we want specifically for GDP for these countries, and we get this matrix. So what this matrix has is each row for each year. So this is 2000, 2001, and so on. It corresponds to each year. And each column for each country in order. The first one is for Portugal, Spain, Italy, and Greece. So this makes it easy to do some comparisons. For example, we load all the files. The way we can do this, we can create a new script for this, just to do these comparisons. And since we have the previous script, so this part with the loading and sorry, not this part, these functions, the indicator values, the loading all files, and so on, all of these functions, we saved this in the Gapminder script, so or module, in the Gapminder module. So this is a gapminder.py. And now if we create a new module, we can import our Gapminder module, and we can also give it an alias. Like we do in Numpy, we can call this gm. So if I want to load all the files, I can just type gm.loadAllFiles, and I'm using the function from the Gapminder module to load all the files from the data folder. And now let's compare the GDP from some countries in Northern Europe, for example, Germany, Norway, Denmark, and Netherlands, and countries in Southern Europe, Portugal, Spain, Italy, and Greece. So we create these two lists of countries, and let's look at the years from 2000 through 2010. Remember that if you want to go from one year to another, in functions like range, or this a range is similar to range but returns a numpy array with the values. So in this case, if I want to stop at 2010, I have to put 2011 here because it will stop before reaching this upper bound. Okay, so I have the years I want, the countries, the northern countries and southern countries, and now I'm going to get the GDP for each northern country. And to do that, I use this getIndicatorValues function that gives me a matrix like this for these northern countries. So for these four that I specified here, and for the years that I asked. And I do the same for the population. So I get the values for GDP, I get the value for population, and if I want the per capita GDP, I just divide one matrix by the other. So since these matrices have the same dimensions, this division is done element by element. And I have the per capita GDP for each year, for each country, by dividing the total GDP for that year, for that country, by the population for that year, for that country. If any of the values in my matrix have not a number, that NaN value, then this division is not possible there, and I get a not a number too. So whenever data is missing, I don't get a value at the end, but I can still do the computation for all the others. This is not an error, it's just then it's missing in the final matrix. Okay, so I do the same thing here for the southern countries, and so I get the per capita GDP for the northern countries, for the southern countries, and now I can compute the ratio between the two. So I can take the per capita GDP of the northern countries, and compute the mean along the columns. So since each row corresponds to a year, something like this here, and each column corresponds to a country, if I project along the columns, I get the mean for all the countries on the first year, on the second year, and so forth. So this will give me a vector. This mean here will give me a vector with the average GDP per capita of these countries, the northern countries, for all the years I'm asking. So it's one value per year. And this is the same thing for the southern countries. I get one value per year, which is the per capita GDP average for these four countries. And if I divide one of these arrays by the other, I get a vector with the ratios along the years. So this would be in 2000, the average of the northern countries was 1.5 times the average of the southern countries, 1.5 here, then 1.48, and so forth. And this is the matrices I get in the per capita GDP for the northern countries and the southern countries. Okay, so today I managed not to cut into the break between the lectures, but I just wanted to recap a bit this part before we move on to the next part. So one thing that is quite intuitive here is that this is a nice result, but it would be better yet if we could actually plot it on a chart or something like that. So this will be the second lecture today, will be about visualizing these data. But for this part, I just wanted to point out a few things. This organization that I did here in the dictionaries and so on was in great part to do a revision of these dictionaries from last week, and also to show you one way of organizing data. So basically, the reason for using dictionaries here is because we started with the potential for having lots of missing data, and dictionaries are very flexible there. We don't need to organize things into rectangular tables. We can just create these trees of dictionaries and put whatever data we have there. So this was the core data structure for storing these indicators from Gapminder. And then going from there, building from there, we created another function that extracts matrices of specific years and countries for when we need to do some operations with the numbers, and it's easier to do with Numpy. So this is the general idea that you need to have, how to organize your data, and then create the tools to change the way the data is structured or whatever for different specific applications in your code. We also saw libraries for reading Excel files and for accessing groups of files on the drive. So the glob library is quite useful for this. That path module in the OS library is useful when you're dealing with file names and want to do operations with file names. So these are examples of libraries that is useful for you to have some familiarity with if you're going to deal with lots of data files. If you have some problem that you only need one data file, then that's not problematic. You don't need this probably. And then we saw the uses of using the Numpy array. So this broadcasting of operations that allows us to do things like this. So compute the per capita GDP for all the countries and all the years simply by dividing the two matrices, or computing the means and then the ratios in this way without having to do loops and for iterating through all the cells and so on. So optionally, if you want, you can look at the Numpy Quick Start tutorial, because it explains better the broadcasting and how to index the matrices and so forth. But this, I think, is mostly one of those things that you will learn by doing with practice. As long as you start using this, then you need to look up the documentation a bit in the beginning, but eventually you start getting into it. Okay, so let's take a short break. We'll continue at 6 p.m. at 1800 with the second lecture. See you soon.